Welcome back, A-level geographers. So this is the EQ3 video of coastal landscapes and change. If you have not watched EQ1 or 2 of these videos, please do so from the link in your Google Classroom. EQ3 looks at sea level change and how that increases risk to coastlines. Please make sure you're using your revision booklet for coasts along with this video. And please remember that this is not replacing what you've already learned. It's not replacing lessons. It won't be detailed enough to get you an A-star in A-level geography. But what it does do is remind you of the key things and content that we covered throughout the course in terms of coastal landscapes and change. So the first thing we're going to look at now is eustatic and isostatic changes in sea level. Now, a lot of students get confused about the differences between both of these. So I'm going to go through each of them briefly, and we're then going to just summarize it as well. So eustatic change then is global. It's due to a volume change in ocean water. It's usually caused by climate change, human climate change and natural climate change in Milankovitch cycles. Decreasing water volume, so water volume lowering, lower sea levels, and increasing water volume makes sea levels higher. In interglacial periods where ice is melting from glaciers, we get rising meltwater from ice into rivers and then into seas, which usually leads to a rise in sea level. So, for example, sea levels rose by 21 centimeters between 1870 and 2010, and we are in an interglacial period. So that's part of the reason. And all of this can lead to what's called marine transgression. Now, that simply means rising sea levels causing flooding of lowland areas by a coastline. Now, to summarize that so far, so the eustatic fall in sea level would mean that it's a glacial period, ice sheets are forming, water is evaporated from the sea and then locked on land as ice, and that leads to a global fall in sea level. But when there's a eustatic rise in sea levels, that's the end of a glacial period, an interglacial period where ice is melting, returning water to the sea, thermal expansion happens, and sea levels rise. So it's just the opposites. When there's a eustatic fall, we're seeing a fall in sea level, and that's glacial periods. And when there's a eustatic rise, we're seeing a rise in sea level, and that is interglacial periods. Now, that's all long-term change over thousands of years. This doesn't happen overnight. And then we come to isostatic changes in sea levels. Okay. Now, this is more local, not global. So isostatic change is all about local land level changes. So rises in local land level cause a fall in local sea level due to post-glacial adjustment, accretion, and tectonic. So for example, imagine there's tectonic plates under a piece of land on the coast of the UK, let's say. And those tectonic plates shift and they cause the land to either rise or fall. That will change where the sea is in relation to that land. And that's the idea with isostatic change in sea level. A fall in local land level produces a rise in local sea level. So as the land level falls, the sea level rises in relation to that land. And that is the basic idea behind isostatic changes in sea level. Let's look at our type of coastlines. So first of all, we have an emergent coastline. Now, an emergent coastline is produced by what's called post-glacial adjustment. That's the movement of land after being burdened by ice coverage. So when ice coverage disappears, land moves because it's no longer held back by that ice. And emergent coastlines are getting bigger and enlarging due to a fall in sea levels, so which exposes more seabed and shoreline, which is the littoral zone or the littoral zone. So emergent coastlines are generally increasing in size. And here on the right-hand side at the top there, we have features such as a raised beach or an elevated marine platform or a sea or a cave or an arch. And what this does is it goes through briefly again what these are. You've already seen these in the EQ2 video and where we can find them. Now, the opposite to an emergent coastline is a submergent coastline. Now, these are coastal zones where the littoral zone is inundated with rising sea levels, like in the southeast of England today. So these are areas where essentially the coastline is disappearing, the sea is taking over, and that reduces the size of the littoral zone, covered in water, seawater, where it previously wasn't. And again here, you've got some features like a ria, a fjord, and a Dalmatian coastline as a result of a submergent coastline and where you can find them. Now, more contemporary sea level change, or sea level change that's happening today due to global warming or climatic change here. So climatic change leads to eustatic sea level rise. Okay, so we know that warming in the atmosphere leads to melting of mountain glaciers like in the Alps and the Himalayas, and that water that melts goes straight into the rivers and down into the sea. That attributes straight then towards sea level rise. So that's eustatic sea level rise. But remember, warming, as I said earlier, also means that there is thermal expansion of the existing ocean water. So when the temperatures of water rises in the sea, that means that the space that that water needs to be stored in increases, which means that the sea level naturally, therefore, rises. So the Intergovernmental Panel on Climate Change, the IPCC there, says that 40% of sea level rise in 1990 to 2010 is because of thermal expansion. It's because of increasing heat in the waters of the ocean. Also, we have tectonic activity, and I briefly mentioned this earlier too. So tectonic activity caused the other 10% of sea level rise in recent times. Obviously, as we said earlier, as the tectonic plates under the ocean shift like a destructive margin, like in the 2004 Boxing Day tsunami, that causes the seabed to move and potentially rise. And if the seabed rises, the water rises with it. It doesn't stay still. So it needs to obviously rise and spread out further, which means it's causing higher sea levels along coastlines. Now, let's talk about the Holderness Coast and the physical factors causing erosion at the Holderness Coast. So you will have done a lot of this in lesson. So at the Holderness Coast, as you can see, there's some images here, and there is some rapid erosion rates, the fastest in Europe along this Holderness Coast. And that's caused by geology and lithology, so rock type and rock structure, and also marine characteristics and the types of erosion taking place. So at the Holderness Coast, we have a soft rock lithology, soft rock type with weak cohesive bonds or weak joints, and we have porous rocks as well. And we also know that the rocks are well jointed. There's lots of joints in them. They dip seaward, they dip towards the sea, and they're heavily faulted. All of these characteristics of the lithology at the Holderness Coast mean that it does absolutely erode very quickly. There is also a large fetch range. There's destructive waves. There's high levels of longshore drift, high levels of sediment being moved along the coastline, and erosion is high too. So all of these physical factors mean that the Holderness Coast erodes very quickly. We also have the idea of human causes of erosion. And your example for this would be the Nile Delta. So the Nile Delta, we're talking about Egypt here, specifically north of Cairo, for example. And what we see here is increased rates of coastal recession. So the coastline is moving further and further inland in the sediment cell. And that's because the dam holds sediment from the river back in it. So that starves the coastline of the sediment it usually gets through natural processes. And if there's not enough sediment being added to the coastline along the Mediterranean Sea, that means the coastline is retreating. It's moving back further and further. So the Aswan Dam there is the example of the dam in 1964 that was built on the River Nile, and that holds back around 15 tons of sediment a year. But also dredging takes place on this river too, and we know that dredging means the removal of sediment from the bottom of a riverbed to reduce the river level. But that also again starves further the coastline of the sediment it needs, and so causing further erosion along both the Nile Delta and also the coastline. Back to the Holderness Coast briefly, and we're going to look briefly at the geology of the coastline, which I've already mentioned, and how weathering and mass movement plays a role there. So Holderness Coast is mainly made up of clay, boulder clays, which are very soft, okay, and they've been left behind after what was the Devensian ice sheet about 12,000 years ago, and they're rapidly eroding. Those boulder clays are weak, little resistance to erosion, and they produce sloping cliffs around 20 meters high. The chalk is stronger. The chalk that surrounds this boulder clay is generally stronger, but of course, once that erodes away, the boulder clay is left exposed, and that's what's eroding very quickly. We have mechanical weathering like freeze-thaw weathering, but also marine processes such as hydraulic action, abrasion taking place here. And over time, therefore, we have what's called rotational slip, which we went through in EQ2 of this GeogPod, and you can see that happening here, where over time there are sections of the side of the coastline breaking away and they're slipping in a rotational movement down the side of the coast over time. Now, there is variations in coastal recession, and they are due to a number of factors. So let's look at what is controlling the coastal recession at the Holderness coast. First of all, we have wind direction and fetch. So we have onshore winds here. We have a long fetch range, a long course of the wind to travel across the North Sea. Destructive waves, strong winds, and that increases all of the rates of coastal recession. So winds from the east, for example, from Russia and the continent, produce recession rates of around 8 meters per year along this coastline, which is a very large rate of coastal recession. We also have the seasons. So the rate of recession is faster in winter in the UK, and that's due to stronger storms and a mixture of hot and cold weather producing more rainfall and higher winds. In Holderness, in winter, 2 to 6 meters of erosion a year takes place. The tides. There is a rapid high and low tide at the Holderness coast. That means there's greater energy and impact on the shoreline. There is also a high level of isostatic change on this shoreline as well, which means higher erosion overall and local sea level changes. And finally, storms. We mentioned these briefly when we talked about seasons. Low pressure events and depressions like rainstorms that we generally get in the UK in winter produce high energy destructive waves, and they increase erosion rates too. So you've obviously all seen choppy seas before. You've heard about boats being cancelled in the Irish Sea, for example, because of choppy waves. This is when storms take place, low pressure events, and that increased amount of energy increases the amount of erosion along the coastline of the Holderness coast, and that means higher erosion rates. Now, generally, who is impacted by sea level rise? Why do we talk about it so much? So it affects a lot of people around the world, and the reason for it is many coastline areas are well populated. They have beaches, they attract large amounts of tourists, they have ports where lots of poorer cities are based. They are generally extremely fertile, so lots of agricultural land is used at coastlines. Generally, you have rivers and deltas and estuaries where people trade through, particularly in LIDC and EDC nations, so they need river access. Generally, also, rivers support mega cities like China, Shanghai, for example, or Bangladesh, or Karachi in Pakistan. So you have lots of people living in these areas by the coast and the rivers going out to the sea. And the IPCC, the Intergovernmental Panel on Climate Change, predicts that by 2060, 12% of the world's population will be living in coastal regions less than 10 meters above sea level. So already there, 12% of the world's population is definitely at risk of coastal recession and sea level rise. Now, you had a case study on Tuvalu. You had one at GCSE as well. And this is the case study of an island that is seeing sea level rise. So there's just some brief points here to pick out from that case study. In terms of height of the land at Tuvalu, it is low-lying. Most places are 1 to 2 meters above sea level. Tuvalu in the Pacific Ocean is no more than 5 meters above sea level across the whole of its islands and has a population of 11,500. And it's very small geographically. They suffer from what's called seawater encroachment. In other words, the seawater encroaching on the land. Okay, so moving in towards the land, especially at high tides. Now, there's some problems that exist in Tuvalu as a result. Subsidence is one of them. Okay, and this is where human activity causes the land to essentially dip and slip. Okay, it causes it to sink. Agriculture, weight of building on landscapes, on compressing sediment, all causes subsidence in Tuvalu. But also we have vegetation issues. So there has been in the past some removal of vegetation on Tuvalu Islands. Now, that's a problem because that removes the structure of the sand and soil, which removes what binds it together. However, recently afforestation has taken place in Tuvalu, and that means that it can reduce the risk of flooding because trees soak up water, but also it stabilizes the sand as well. Now, next we're going to look at storm surges briefly. And a storm surge, remember, is a temporary rise in sea level produced by a storm or a depression or a tropical cyclone. Okay, so it makes the sea level rise due to the wind height, uh, falling rainfall, and so on. Now, please be aware here that you must do the case studies you did in lesson, but I've got two examples from the ones that we have often done in the past here. So first of all, Bangladesh, and that was Tropical Cyclone Cedar in 2007. So this was a Category 4 cyclone or tropical storm, and it had 6-meter storm surges. And the impacts were worsened of this by deforestation that has taken place over the years, removing mangroves from coastal areas, intense rainfall, and unconsolidated rocks and materials along the coast. 60% of Bangladesh is low lying, so that's another issue in terms of having a storm surge. In this event, 15,000 people were killed and 55,000 were injured. 1.6 million homes were destroyed. 8,000 kilometers of road, 700 kilometers of electricity lines, and 900 freshwater wells were destroyed. And the estimated total damage of this storm surge was 1.7 billion US dollars. So a very expensive damage list from a storm surge, which caused local sea level rise as a result of depression slash tropical storm surges. Now, another example just to compare that is the UK. Now, Storm Xavier in 2013, which some of you may remember, caused 80-mile-an-hour plus winds. And the storm coincided with what was called spring tides, which is a high tide during spring. 3 to 6 meter storm surges, therefore, existed. Now, the North Sea is a particular interesting geographical region because it funnels water towards the coastline. So that funneled the water towards the coastline, causing severe flooding along that coastline. Now, 2 people were killed, 18,000 people evacuated, and 1,400 homes were flooded as a result of this storm surge in a developed nation. And the East Coast Railway line was suspended for a day. Total economic cost of this storm and storm surge was estimated to be around 100 million US dollars. Now you can see the differing impacts there of coastal issues like storm surges in a developed nation in the UK versus a developing nation in Bangladesh to be able to make a comparison between them. So the next thing is quite detailed here, and this is the Intergovernmental Panel on Climate Change report of 2014, looking at the progress of global climate change and what the likely risks are for the future. So it was a projection report with confidence levels on the right of what would happen for each factor. So let's start with sea level, the risk of sea levels rising. The projection is that sea levels will rise between 18 and 59 centimeters by 2100. Now, the pace and the range of that rise is uncertain. And adaptation and management strategies are in place in a lot of countries around the world. So it's very hard to tell how many people may be severely affected by it. But there is a high confidence that the sea levels will rise by 2100 by at least 18 centimeters and possibly more than that. Delta flooding. So this is where flooding happens where rivers meet the sea. and this is likely to increase by 50% in some of the world's major deltas. There's a high confidence of that happening. So the next thing is wind and waves. Now, wind and waves are key to causing damage from climate change, but also may increase due to the fact that climate change increases the instability of our atmosphere. So there is some evidence that wind speeds are increasing, and there have been larger waves in general due to the stability of the Earth's climate. So we've got medium confidence that that may continue. The next one is coastal erosion. There is a medium confidence that coastal erosion will continue to increase because of the combined problems above. So weather patterns changing, weather systems changing, sea levels rising, and weathering impacts. So all of this means that coastal erosion is likely to continue to rise. Next, we're going to look at tropical cyclones. Now, we are less confident, and the IPCC is less confident in the projection for this, but they have still considered it. The frequency of tropical storms is likely to stay the same. So they're likely to be as regular as they currently are. But the size and scale could increase. So the strength of them has already increased in recent times and may increase by 2 to 11% by 2100. Now, ocean temperatures are rising. So that means generally the strength of these is likely to increase. The higher the ocean temperature, the more likely, the more intense the storm. And finally, then, of low confidence again, is storm surges. So we know that storm surges are caused by storms, depressions. Now, those depressions are likely to become more common due to an instability in our world climate. And that means that potentially there is more of a coastal flooding risk as more storm surges are likely to take place, although there is low confidence in exactly how many or where will be mostly impacted in the world. So this slide is just a summary of the projections by the Intergovernmental Panel for Climate Change in 2014 of what might happen by 2100 in terms of the flood risk factors on the left. And that is all of EQ3 covered there in a brief manner. Please do look back over this, make notes as detailed as you can on this, and refer back to your lesson notes. The next GeogPod will be on EQ4, the final EQ of coastal landscapes and change, looking at players involved in coastlines and how coastlines are managed. Please do ask your teacher if you need any help with anything in EQ3, and I'll see you in the next one.